now we start next part of our discussion, and what we want to talk about really is, we have been using and we have demonstrated when we went to the lab and we talked about it, we have been using nonlinear optics quite a bit. In the last module, we had talked about your amplified laser, the laser that we have. The next step is the optical parametric amplifier. Now, in order to understand optical parametric amplification, first of all we need to build a little bit of basics of nonlinear optics. And as has been the central theme of this course, we are not going to try to derive everything perhaps, but we will try to understand how things work. So, what we learned today is this: when we showed this femtosecond optical gating experiment, we had shown that red light comes, falls on some nonlinear crystal, and then when we turn the crystal by using a micrometer screw, we see that second harmonic is generated to a greater extent. So, today in this module, we are going to learn why that happens. Why is it that you turn the angle of a crystal and you get good second harmonic, while you do not get it earlier? To do that, we have to, I am sure many of us know already about nonlinear optical phenomena. So, we will discuss the basics and let us see how far we can get. So, first of all, we have talked about this earlier, and I am sure everybody has learned this in other courses. The model of interaction of light with matter is that light induces a polarization in the medium. The electric field component of light induces a dipole moment, electrical dipole moment, and that is what interacts with the electric field to give you the radiation matter interaction, which is what we are talking about throughout. Now, if you have ordinary light, then you have linear response, meaning the polarization is directly proportional to the amplitude of the electric field E. So, we can write it in a very simplistic manner as P equal to chi first order, that 1 in the superscript within bracket means first order. It is not chi to the power 1, it is not chi 1, it is chi first order. So, P equal to chi first order E, where P is polarization, first order chi is the electric susceptibility of first order, and E is the amplitude of the electric field. But then there is actually more to this than what we have written. Can someone tell me what more is there? What is it that we are actually hiding in this simplistic expression? No, that even before going to square cube term, even in linear response, suppose the response is linear, I am saying even then in that case, this equation that we have written is a tad too simplistic. The situation is more complicated than that. Okay, hint Raman spectroscopy. You have learned this in Raman spectroscopy. Yes? No, not dipole moment, susceptibility. So, let us say alpha, instead of chi first order, I will write alpha, polarizability let us say. If I write polarizability, does that ring a bell? Think of what you learnt in Raman spectroscopy. This expression is actually more complicated than what it is. Okay, electric field, is it a scalar or a vector? It is a vector field, right? What about polarization, scalar or vector? Yes. So, now Prajit has remembered, the thing is this, it is not necessary that if I apply an electric field along x direction, polarization will be along x direction only. Electric field along x direction can produce polarization in other directions as well. So, if you write P, the three components of P, Px, Py, Pz, let us say we write it as a column vector, column matrix, that will be equal to column matrix Ex, Ey, Ez left multiplied by a square matrix, right, and the components will be something like alpha xx, alpha xy, alpha xz and so on and so forth. Why is it that if I apply electric field along a particular direction, polarization is produced in other directions as well? Yes? I am applying in one direction. So, to answer this question, the easiest approach is to think like a baby, like a kid. Think of simple analogies, it is easiest to understand that way. Okay, what is the meaning of polarization? Production of dipole moment, what is actually happening to the molecule? Electron, right? So, electron, is it a particle or wave or what? Right. So, electron cloud, and the electron cloud is distributed all over the molecule. So, when you polarize, what you do essentially is that you distort the electron cloud. Is that right? So, let us say we have spherical electron cloud over the molecule, you distort it so that in one direction the concentration of electron cloud is more, in the other direction it is less. Okay. I like to think of it as a balloon. This entire electron cloud is like the air contained inside a balloon. Now, think of holding a balloon and pressing like this. Well, you can pull also, but then it is easier to press. So, this is the field you are applying, and the balloon will get depressed in this direction, but is it not elongated in the perpendicular directions x and y? Yeah. So, that is a rough analogy that explains why when you apply an electric field in a particular direction, distortion takes place not only in that direction, but also in perpendicular directions, all directions. That is why it is actually a tensor. For our purpose, for now, it is okay if you write like this. Right. Next, we come to what Shoradip was saying. This expression that we have written in simple form or in matrix form, this is valid when we have ordinary light coming out from the electric bulb, where the field is weak. What happens when we use a laser? A laser is associated with significantly higher electric fields, right? Then the response is no longer linear. Then you have something like this. You have a nonlinear response, P is equal to chi first order E plus chi second order E square plus chi third order E cube, and so on and so forth. And the reason why you see this for high values of E and not for low values of E is that first order chi is much larger usually than second order chi, if it is provided the second order chi is non-zero, we will come to that. Second order chi is generally much larger than third order chi, and so on and so forth. So, that is why unless this E square term or in some cases E cube term can take over, unless the value of E is sufficiently large, you do not see the higher order terms. Okay. But when you deal with lasers, you can get at least the second order term. Sometimes you can get the third order or fourth order term as well. We will see what are the conditions that are required for these higher order terms to be involved. Okay. For now, let us focus on the second order chi. It is called the second order nonlinear susceptibility. Okay. So, this is the beginning of our discussion of multiphoton processes. Two photon process, of course, is the simplest multiphoton process one can think of, and the second order nonlinear susceptibility is responsible for bringing about two photon processes. So, once again let us remind ourselves of what two photon processes are. So, whatever we are discussing now, I believe is known to all of us, it is just a recapitulation. What is the meaning of two photon absorption? Let us say we have these two energy levels separated by an energy equivalent to frequency of 2 nu or nu 1 plus nu 2, depending on whatever we are going to write. So, to start with, let us say the energy gap is equivalent to frequency of 2 nu, and let us say I excite with laser pulse of, or not necessarily pulse, laser light of frequency nu. What will happen? The photon does not have enough energy to cause a transition to the next available stationary state, right. But once again, cutting a lot of mathematics out and using a little bit of childish analogy, the molecule does not know, right. The molecule does not really, the molecule has not studied quantum mechanics. So, it does not know when the light comes that it is not supposed to absorb it. So, what happens is the distortion of the electron cloud starts anyway, and then it reaches some virtual state. What is the virtual state? What is the stationary state? What is the virtual state? What is the stationary state? CH107. A stationary state is a state in whose energy or whose psi star we can say is independent of time. Okay. So, these are states associated with finite lifetime. Your molecule can stay there for some time, and virtual states are anything in between. You can have an infinite number of virtual states between any two stationary states, and the way you generate these virtual states is by taking linear combination of stationary states. And the point to remember is that virtual states are associated with lifetime of 0. The molecule cannot stay in the virtual state for any amount of time. So, the moment it is there is going to come down. So, if your intensity of light is not too much, then you will not see any absorption. So, you can think like this: the electron cloud starts getting distorted. This is the shape of electron cloud in the ground state. This is the shape in the excited state. It starts getting distorted, runs out of gas midway and comes back. However, if you use intense laser light, then what happens is, at the same moment when the molecule or well let us say the system is promoted to the virtual state, there are many other photons around. So, a second photon can cause promotion to a second to the stationary state. And if you carefully choose the frequency of the photons you use, so that their energy is exactly half of the energy gap between two stationary states, then you can have what is called 2 photon absorption. Okay. So, this is a very simplistic hand waving way of saying what 2 photon absorption is. And the case we have discussed is the simpler of the two cases of 2 photon absorption, where it is where both the photons have the same color, same energy, same frequency, degenerate 2 photon absorption. That need not be the case always. Sometimes what happens is that the energy gap might be equal to the sum of the frequencies of 2 different kinds of photons that you have at your disposal. In that case, first photon, let us say nu 1, takes the system to the virtual level, and at that instant a large concentration of nu 2 photons are available. The molecule is promoted to the next stationary state. Of course, all this is just wishful thinking. We are writing like this to understand. There is no reason why nu 2 will not be absorbed first. We do not know actually which have been absorbed first, which has been absorbed first. The other analogy I like is that it is sort of like 2 water droplets joining up together and forming a larger droplets. So, energy of 2 photons are sort of getting added up to give you the promotion that you require. Okay. So, so much for 2 photon absorption, but then when absorption takes place, the energy of the system goes up. So, anything that goes up has to come down. So, let us talk about some frequency generation, or in some cases 2 photon excited fluorescence. Let us take the second case, where the energy gap is equal to nu 1 plus nu 2, non-degenerate 2 photon absorption. Now, and let us say that the energies of nu 1 and nu 2 are such that nu 1 plus nu 2 is not equivalent to any energy gap between two stationary states. In that case, even after nu 2 is absorbed, the system is going to reach some virtual state, right. What is the lifetime of a virtual state? 0. So, the moment the system has reached that virtual state, it cannot stay there. Immediately it has to come down, and it comes down with emission of the light that is absorbed. But then there is no memory. The system does not remember that I had absorbed nu 1 first and nu 2 second, or the other way around. There is no memory. So, when the emission takes place, the emission is of a single photon of frequency nu 1 plus nu 2. This is how some frequency generation can take place. Now, think of a case where this higher energy state is not a virtual state, but rather a stationary state. Then what will happen? Stationary state, is it associated with some non-zero lifetime, or is the lifetime 0? generally lifetime is not 0. So, when the molecule gets excited to a stationary state and then the emission takes place from there, what is it called? Fluorescence in the simplest case scenario, yeah, same spin multiplicity. So, this is something that is used especially in microscopy, where you excite, where you do a 2 photon excitation and you look at the fluorescence. The problem is this, let us say I want to look at some protein under a microscope. What are the fluorophores in protein? Generally, tryptophan is the major one, anything else? Tyrosine, anything else? Phenylalanine, this is something that is perhaps the least popular. There is a school that has tried to promote tyrosine as a good fluorescent probe and all, but generally people follow tryptophan emission. Okay. If I want to follow tryptophan emission, where do I excite? 295, but tryptophan absorption maximum is 280 nanometer. Why do I excite at 295 nanometer? So as to avoid exciting phenylalanine and tyrosine. Okay. So that is just a recap, not really anything to do with the present discussion. Now, the problem is this, I want to look at a protein that is inside a cell under a microscope and I want to follow it by tryptophan emission. Then I have to excite by 295 nanometer light. Two issues there. First of all, unless you buy a significantly more expensive UV microscope, regular microscope optics are all glass. So, 295 light will not even get through. Secondly, even if you use a UV microscope, you are looking at cells which is a turbid medium, they are going to scatter light. Scattering efficiency, how does it fall off with lambda? Lambda to the power what? Lambda to the power 4. So, these are things we cannot forget, we have to remember. So, UV light is scattered big time, so you will not see anything. So, it is much better in that case to not use 295 nanometer light, but rather use some laser which gives you 295 into 2. How much is 295 into 2? 300 into 2 is easier, 600. 600 minus 10, 590. So, 590 nanometer laser, if you can use intense 590 nanometer laser, then you can have a 2 photon absorption to a stationary state, right, and then you can look at the emission of the protein, provided that emission is not scattered, provided that emission provided your optics that can look at that emission, that is a different issue. 2 photon excited fluorescence is very popular in biological systems, because the problem is this, if you use wavelength that is too short, it will get scattered, if you use wavelength that is too long, it will be absorbed by water. So, typically when one wants to do microscopy, one wants to work in the therapeutic range of 650 nanometer to 900 nanometer. But then if you excite at 700 nanometer, where will it emit? It will emit beyond 900. 2 photon excitation followed by fluorescence is a very popular technique, especially in microscopy. Okay. But here, coming back to our present discussion, what we have seen here is how you can get some frequency generation. So, in some frequency generation there is no delay, light is absorbed instantaneously, light comes out instantaneously, you do not have to wait any time. So, if nu 1 plus nu 2 is the case, we call it some frequency generation, and in the special case where nu 1 and nu 2 are equal to each other, then we get second harmonic generation. That is what we do inside our millennia laser, that is what we do for in the fog instrument and in many other places. Okay. So, now with that simplistic background build, let us go a little further into understanding second order nonlinear phenomena. Okay. So, once again we are following this our usual textbook, Helena. Now, think of what you have in the entrance side of the fog spectrometer. You have light from a laser, here we have written with frequency of omega, it falls on some nonlinear crystal. We will talk about what optic axis is in a little while, and then you get omega and 2 omega out, and then you use a long pass filter to get 2 omega out and block omega or do something. In our case, what we do is we transmit omega and we reflect 2 omega, fine, but you have to use a dichroic. Here once again we proceed in the simple with the simple description of the system. The electric field of light is a function of position as well as time. That R that we have written, remember anything that is in bold is actually a vector. Electric field is a function of position and time, and it is given by E0 multiplied by cos of k1 r minus omega 1 t. What is omega 1? There is no need to write omega 1 here actually, I could have written omega, but later on I have talked about omega 2 and all, that is why here omega 1 is there. What is omega? The answer is there in the projection. Omega is the angular frequency of light, incident light. Okay. What will be angular frequency of the second harmonic? 2 omega, remember. Okay. What is R? R is in bold, so it is a vector. What is that R, small r? There are very few things for which you use R and a vector at that. What is R? Okay, just tell me, what do you use small r for? Distance, right? And R vector, does that ring a bell? Distance from where? It is a position vector, distance from the origin. You have some point x, y, z, you draw an arrow from the origin to that point, that arrow denotes the position vector. R is that same position vector, nothing else. What is k1? K1 once again is a vector, it is called the k vector. Is there another name that you know? Wave vector. So, what is k? That is something that we should say, and then we can stop this module, go to the next one. We will come back to that. But first of all, suppose this is E, and for this expression of E, I want to write the expression for this second order polarization. What will it be? Just the second order term, not the first order term. Remember what it was? P equal to chi first order multiplied by E plus chi second order multiplied by E square. So, what will be the second order term for polarization? Chi second order multiplied by, well, E square. What is E square here? E is equal to E0 cos k1 r minus omega t, omega 1 t. So, what is E square? E0 square, that is a good beginning. Then cos square k1 r minus omega 1 t. It is very simple. So, as I have said many times in many different fora, I never ask difficult question, cos square term. But now I want to ask a question, let us see if you remember our high secondary trigonometry. How do we write cos square theta? Cos square theta is equal to, well, in terms of cos, since we are writing cos, we will stick to cos, 1 plus cos 2 theta divided by 2, right, 1 plus cos 2 theta divided by 2. What is theta here? K1 r minus omega 1 t, right. So, can you work out the expression E0 square, do it in terms of theta, E0 square cos square theta. What does it become in terms of cos 2 theta? E0 square cos square theta. If I want to write it in terms of cos of 2 theta, cosine of 2 theta, what do I get? Yeah, E0 square by 2 plus, you have taken 2 common, plus, there is a half as well, and do not forget second order chi, I might have forgotten to say it. Okay, so well, okay, that will come later, fine. E0 square by 2 plus cos 2 theta divided by 2, okay, that is E square. Now, to get second order term for polarization, this term has to be multiplied, this factor has to be multiplied by second order chi, second order susceptibility. So, this is the answer. Second order term for polarization is given by second order nonlinear susceptibility multiplied by E0 square by 2 plus half second order nonlinear susceptibility multiplied by E0 square cos 2 theta, where theta is k1r minus omega t. Okay. What is the frequency of this associated with the second term? What is the frequency, angular frequency associated with this second term, this one? 2 omega 1, that is right. So, look at the first term. The first term is a constant polarization, is not it? There is nothing in T there. It is just second order nonlinear susceptibility multiplied by E0 square by 2. E0 is a constant of time, constant of space, constant of everything, right. So, this is called constant polarization or DC effect. This part is used to measure the power. Second one is actually the second harmonic term. There you have a polarization that is modulated by a frequency of 2 omega 1. So, this is the term that is responsible for second harmonic generation. Okay. Then we take a break here, and in the next module we start right here.